if we continue the procedure, okay, we can get in the final step V11, since we already calculated V31 and V21 by using the equation 2V11 minus V21 plus 0 V31 equals to 1. In this way, we will end up with knowing the first column of A minus 1. I will repeat with you in detail the procedure for the second column vector, okay? And you will continue with the third to be able to calculate A minus 1. So now we know the first, this first column of A minus 1. We will move now to find, so in the next step, we will find what is V12, V22, and V32. This is our second element, second vector to determine. Okay. Now let us do the procedure together again. So now what will change in the procedure? My matrix L and U are the same. Just I'm changing here vector B, because vector B, when I use the first column of A minus 1, I use the first column of the identity matrix. Now, what I will do, I will replace V11, V21, V31. I will replace it by this vector. Okay, so now I want to find these unknowns, which is the second column of A minus 1. And then as a result, I expect to have the second column of the identity matrix, which will be, here I will have a 0 instead of 1. Here I will have 1, and here I will have 0. Okay, so the updated B vector now will be 0, 1, 0. Okay, now the steps will remain the same. First, I should do forward substitution. So I will use now matrix L, which I got in the first procedure. Now I have three unknowns. I can call them what I want. يعني فيني خليهم اسمهم D1, D2, D3. Okay. If you want to just because you know that you are finding several vectors, if you can summon D prime 1, D prime 2, D prime 3. No, no problem. Just it's the way you name them. And equals here, instead of 1, 0, 0, it will be, I will replace this vector by vector 0, 1, 0 now. So now 0, 1, 0. Let me check the questions. Why we didn't use regular Gauss elimination with back substitution and we just changed matrix B? Because Muhammad, if you want to use the regular Gauss elimination, when you do the forward substitution, you will use the augmented matrix. So at each time you will have to update the coefficients of A and the coefficients of B. So you are repeating then the operations again. Okay? This is why we say that in order to not have to repeat the forward elimination and how the coefficients are changed in each step, then we use the LU factorization. Okay? Because try to do it. If you use a regular Gauss elimination, if you want to find what will be the updated B, you need to proceed, you need to do again the forward elimination. Okay, and this will take time. So not to do this, we decouple the two processes. We find first L and U, which will be used in each operation, and then if B changes, we don't have to do any forward elimination again. We just have to do forward and backward substitution. Okay. So now, once we have this system, we will write the equations. We will write our equations. Okay. So the first equation will be. So let us repeat the equations together. Okay. So the first equation we get will give us D prime 1. To get D prime 1, we have 1 times D prime 1 plus 0 equals to 0. So the first equation will give us that D prime 1 is just equal to 0. So we are done with d prime 1. Now we move to d prime 2. Okay, for d prime 2, now we use the second equation. From second equation we have 0.5 times d prime 1, but since d prime 1 is 0, so this is 0, plus 1 times d prime 2 is equal to 1. So this will give us that d prime 2 is equal to 1. And we are done with the second unknown. Now we move to d prime 3. Okay, to calculate d prime 3, we will use now the third equation. So if we write now the third equation, we will get 0 times d prime 1 plus 0.4 times d prime 2, and d prime 2 is already calculated to be 1, so times 1, plus 1 times d prime 3, so plus d prime 3, equals to the third element here, which is 0. So you conclude then that d prime 3 is equal to minus 0.4. Okay, so now you are done with vector d prime. So now you can replace vector d prime by 0, 1, minus 0.4. So this is what you will do here. You will replace here vector d by its expression. So I have 0, 1, minus 0.4. And now I am doing the backward substitution, but now to get v, now I am getting the second column, so v12, v22, and v32. Okay, and here, since again I will do backward substitution, I will start from the third equation. If I start from third equation, I get that 2.8 v32 is equal to minus 0.4. So I get the value of v32. Once I'm done with v32, I move to the second equation. The second equation will give me 2.5 v22 plus 3 v32 okay, is equal to 1. And now, since already I got v32, I replace back here and I get v22. And finally, I use the first equation, which is 2 times 0, 2 times v12 minus 1 times v22 plus 0 times v32, and then I get equals to 0, and then I get the value of v12. And please, I advise you to practice with this example. So we did together the first column of a minus 1. We did together the second column of a minus 1. Try to do the third column of a minus 1. And then at the end, to verify that your result is right, you do the multiplication a times a minus 1. You should get the identity matrix. Okay. Of course, because of some numerical errors, you might get something that is very close to it. And now we will talk about this. We will talk that certain times, if I have a nil conditioned matrix to a high degree, I can obtain, when I do a times a minus 1, I will not obtain the identity matrix. This is because of round-off errors that we will introduce now. Any question on how we find a minus 1 before proceeding? Okay. So now let us go back to our PowerPoint. So we have seen how to use a minus 1, and we have seen together here how to compute the inverse of the following matrix. So please make sure to complete the example and to do a times a minus 1 to check if your result is right or not. Now what we will do error analysis and system condition. If you remember, when I introduced for you chapter 9 and the possibility of solution of a linear system equation, we had 4 possibilities. We said we can have no solution, we can have infinite solution, we can have just one solution, and the fourth possibility was to have a nil conditioned system. And then we defined the ill-conditioned system as a system in which if we vary by a small amount vector b, the solution will vary in a drastic way. Okay, this is why we said that this is due to round of errors. Okay, and to understand this more, we can see here. So if you remember, we said that in this case, the determinant of the function of the matrix will be very close to 0, which will cause some problems in the solution. Because if you recall that if the determinant is 0, no possible solution. But if the determinant is close to 0, this also we can have solution, but we cannot trust it a lot. So now, in order to be able to do the error analysis and define the system condition in a number instead of saying this matrix is very ill conditioned or is not very ill conditioned, we need to define a certain number to assess the system condition. So first, before defining this number, we will talk about what is well conditioned or ill conditioned. So a matrix inverse can provide information about the condition of the matrix. It is well conditioned, very well conditioned, ill conditioned, not a lot. And as you can see from the terms, very ill conditioned or little ill conditioned, it's not a binary state. It's not or 0 or 1. So or it's ill conditioned or it's not. You have a range to define the illness of a matrix, the ill condition of it, because this is first, it can be subjective. It depends on your application. For certain applications, this matrix can be acceptable, while for others it is very bad. Because here you have a range to define what is ill condition. So you can also compare matrices to say this is more ill conditioned than this. So you have a range of definition. It's not just or ill conditioned or not. And we have several criteria, several measures that we can perform to make sure if my matrix is the degree of illness, if you want, of my matrix. So what are the criteria that I can use to say that it's very ill conditioned or less ill conditioned or more? So we need to define some techniques. The first technique is to normalize rows of matrix A to 1. What we mean by normalizing the rows of matrix A to 1 is to consider the largest element of a row, and then we divide all elements by this element. And then we end up with the highest element will become 1, and all other elements will become lower than 1. This is called scaling the elements row by row, okay? So that the largest element in each row is 1. And once we do the scaling process, we find the inverse of the resulting matrix. So I have a scaled matrix, and then I calculate its inverse. Now, if in the inverse I have elements that are much larger than 1, this matrix is likely ill-conditioned. And higher is the elements, and if I obtain higher and higher elements, so I can compare in this way which matrix is more ill-conditioned. If I have elements that are very far from 1, this means that it is the matrix I am dealing with is more ill-conditioned. Okay. A second criterion is to calculate A times A minus 1. In general, you expect A times A minus 1 is the identity matrix. But because of numerical errors, because of round-off errors, it will not give me 1, the identity matrix. It can give me something very close. If I do A times A minus 1 and I get exactly I, this is a extremely well-conditioned matrix. Matrix A will be extremely well-conditioned. If I get something that is close, acceptable, close to I can say it's well-conditioned. Now, if I'm getting something that is very far from I, so I have a very ill-conditioned matrix. And as I told you, you can compare the illness of the matrices by this factor, the degree for which it is close or not to I. Okay? And the third criterion, the third method is to do the inverse of the inverse. I get first the inverse of a minus 1. Then once I get it, I do the inverse again. I expect to get a. But if I get something that is far from a, this means that I have a certain illness with my matrix. Okay? Of course, this will require a lot of time, so I don't advise you to do it unless we ask you to do it. So in general, this can be easier. So just you get a minus 1 and you multiply a times a minus 1. It's easier than doing inverse 2 times. Okay. Now we will take some examples together and we'll do their analysis just to see how we can judge nearly the degree of illness. But then we will not always obtain, we can compare in this way matrices, the degree of illness of matrices, or say that it's likely ill condition or probably ill condition. But to be sure of the degree of illness, we will develop together next time a method to calculate the condition number. And the condition number will give us, if you want, a precise method to evaluate the degree of illness of a certain matrix. So now to start with the first criterion. Okay, so imagine I have to use I have this matrix A. It's a 5 by 5 matrix, and I want to test using the first criterion if this method the degree of illness, so if it's likely ill conditioned or not. Okay, let me check just for your questions. No, George. It's hard to tell if it's ill conditioned just from the initial matrix. Okay, it's not easy to do it. So we need to perform these operations to know. Okay, so first, as the first step in order to normalize. Okay, what is the idea? First, I look for each row. I normalize each row. So I will start by finding what is the highest element in this row. Since here the highest element is 1, it's great. No need to do anything. So in my scaled matrix, the first row will remain as it is. So 1, 1 over 2, 1 over 3, 1 over 4, and 1 over 5. I don't have to do anything. It's already scaled. Okay. Now I move to the second row. What is the highest element in the second row? It's 1 over 2. So now, in order to scale my row, I should divide all terms by 1 over 2, or which is equivalent to multiply by 2. Because when I do so, then the first element will become 1, and all other elements will be lower than 1. So here I multiply by 2 all remaining elements. I get 2 over 3, 2 over 4, 2 over 5, 2 over 6. Okay. So this is my updated row here. Now I will repeat the procedure for all rows. This is a particular type of matrix because I will have all the highest elements are always in the first column here. But it's a particular case. So I can give you any matrix. When you do the scaling, one can be anywhere. Okay, so here it is a particular case. This is why always you have 1 in the first column, because you have the highest element in the first column, but it can can give you a different case. So 1 can be anywhere. It will correspond to the highest element between the elements of the row. Okay. So here, if you proceed with with normalizing each row, you will end up with the following matrix. Here it's not written. I will update it for you. Okay, in the slides I will put it for you. So we can write it together here. So the updated matrix will be 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, And already here you multiply all terms by 2. Here you multiply all terms by 3. Here you multiply all terms by 4. And here you multiply by 5. I think I was doing it for you here. Okay. So as you can see here, if you are done with the normalization process, this will be your updated matrix. Okay. So here it will remain as it is, and as we said, we multiply here by 2. For example, here you multiply by 5, so you get 1, 5 over 6, 5 over 7, 5 over 8, 5 over 9. So now this is the updated, this is a normalized, this is a scaled matrix. Now the strategy is to find b minus 1. I advise you to do this exercise to make sure that you know how to do LU factorization. So now, if you want to proceed to get b minus 1, you should repeat the same method we did. Now to get, and you will do LU factorization first to find what are the equivalent lower and upper matrices of this one. Here, for example, you can test if you can use Cholesky method, because if you, it's not also here the case because you don't have symmetry. Okay, so if here when you do the scale, after doing the scaling process, you don't have symmetry, but before doing the scaling process you had symmetry. And this is why it might be good to not use this method, to use, for example, the second method of testing the illness, which was to do a times a minus 1. Because here, for example, look, you have symmetry, okay? Because if you look at the diagonal, you have elements are symmetrical. So this will help you if you just have the step to verify that it's positive definite. So once you verify that it's positive definite, you can use Cholesky method easily. So if in case it was positive definite, so but maybe the process to find that it's positive definite is long. So in general, I can tell you myself that using Cholesky factorization, let's say, find the lower and upper matrices equivalent. So here you can use, in case we can demonstrate it's a positive definite matrix, so we should test for this. So if I test for this and I am sure, then I can use Cholesky method to find in a simple way, because I can just say then that I can decompose it into upper and times upper transpose matrix. And we have seen last time that it's very easy to get to U. Okay, so if you recall the Cholesky method, it is much easier than performing LU factorization. So we should check if this is possible or not. And as I told you, in general, I will tell you, because it's not easy to check for a 5 by 5 matrix. You need to do a lot of computation to make sure that it's positively definite. It's positive definite. So let us consider in case it verified the two criterion and we can use Cholesky method, then you can find L and U in an easier way. Okay, so then you can get in this way you can get LU using Cholesky, and then you can proceed in a similar way that we did to get matrix A minus 1. Okay, and once you get A minus 1, what you do at the end, you multiply, you verify if in A minus 1, if A times A minus 1 is close to the identity matrix or not. Okay, so this is the second method we developed to check how the L condition of a system, of a matrix. Now let us proceed with their method. So we are using the scaled method. So first we normalize each row, and then once we get the updated B. Now of course it's not symmetric, and we cannot use Cholesky. So of course we should use the conventional LU factorization technique. We can use it as we did in the example together. I advise you to try it, okay, to find the 5 columns of B minus 1. So here it will take more time because the system is 5 by 5. So you need to do a LU factorization procedure, backward and forward substitution. You should do it 5 times. You just do 1 time LU factorization to get L and U, but once you get L and U, you should do forward and backward substitution here 5 times to come up with your resulting B minus 1. Okay. Now, as you can see here, I have very large numbers. and then I have, for example, the largest one. Sorry, are you asking me a question? Okay, so here, for example, the largest element is this one, and it's really large, and all elements are very far from one. You can say that it's you have a high ill condition here because all your terms are far from one, and you have terms that are very, very far from one, which is not good. Okay, so now, as I told you, you can have more ill conditions, still more. If you have higher values here, let's say instead of 39,000, if you have the number 300,000, so it's still more ill conditions than this matrix. So this is how, if you want, you can compare. But just when looking at it, it seems that it's not. It's an ill-conditioned system. It's highly ill-conditioned because it's your elements are very far from one. Okay. So this is the first method we developed to test the condition. Now, another method will be to, instead of normalizing, as I told you, to get A-1 from here, using or Cholesky if possible, or LU factorization, and then multiply A times A-1. If I get a matrix that is very close to the identity matrix, then I can say it's well conditioned. If not, I can say it's most likely it has high ill condition. Okay, so now let us try another example to see how to apply the second criterion. Just let me check your questions. No, Leah, do you mean do we have to pivot in which stuff? Sometimes yes. In LU factorization, you might need to pivot. In the example we have taken together, it was already very well arranged, so we didn't have to do any pivoting. But sometimes when you perform a LU factorization, in case you have to do pivoting, if you remember, we introduced the permutation matrix. So then you should find the permutation matrix, and then whenever you have a B vector, you should use P times B. We already have done an example on it in previous session. Okay. So yes, you should always test if you should do pivoting or not whenever you do the LU factorization procedure or Gauss elimination.
Yes, أنا قصدي بماتريكس B لأنه when you log all the first equations بس العملة الأولى بيصير هونيك في 0.5 ومن تحتها 0.3 وهيك so إنه it would be better if you pivot.
Yes, no? of course. نحن هون we just said إنه we will determine B-1 ما قلنا كيف. But if you follow the procedure, أكيد you might need to do pivoting, of course.
Okay. Yeah.
Okay. Any other question? Yes.
هلا بس لنطلع البي inverse.
Yes.
We compare the values of this matrix مع مين؟
مع 1. لأنه نحن قلنا ما نحن ليش عملنا scaling هون؟ تيكون عندنا one largest element. So here, when you do B-1, if you have elements that are close to 1, not very far from 1, this means that your matrix is well conditioned. But if you obtain very large numbers here, this means that you have a likely ill-conditioned matrix. Okay?
Yes, doctor. Thank you.
Well, okay. Now, second step is to do. Let us take another example. So let us go back to our.
عندي سؤال.
No. Yes.
الإكزامبل الأول لما you defined إنه شو يعني ill-conditioned هو كان system طلع إنه solution changes كثير.
نعم صح. Exactly.
بس هون ما إنه system هون matrix لحاله إنه.
بس ما أنت هالماتريكس كيف حتستعملها؟ حتستعملها for it to solve a linear system. يعني أنا إذا بعطيك A times X equals to B. How you test the ill condition of the system? The ill condition of the system will depend on matrix A. فساعتها أنت بتاخد matrix A and you test it. Okay?
يعني ما خاصة بالvalues of B إذا قراب على بعض أو هيك شيء.
لا ما خاصة بالبي أبدا. انت B you can vary it, but you can إذا you vary B مثلا one term of B by 1%. انت you expect انه إذا solution is fine, إذا system is working in an appropriate way, ما مفروض X to vary a lot, صح؟
صح.
بينما إذا A is in a conditioned matrix, it can vary a lot. إذا بتتذكر examples that I gave you, we varied B by 1%, طلعنا variation of X by sometimes by 100% and more sometimes, which is very bad. Okay, this means that you cannot trust your system even in 1%. If you have 1% uncertainty in B, you will get a very high uncertainty in X, which is not practical. Okay, يعني مثلا in experiments, you know, when you perform experiments, هيدا vector might be is prone to errors, and you can have errors up to 5-10% experimentally. So if you have a matrix A that is not very well conditioned, this will cause a very bad solution, and you cannot trust your solution in this case. This is why, in general, this is why we will introduce in this chapter how to test the condition of matrix A in order to expect if we can trust the solution and to what degree we can trust it. Okay.
Okay, thank you, doctor.
Welcome. So now, for example, yes.
بس small question. إذا طلعنا determinant وطلع قريب للزيرو, could we يعني confirm أو لا?
Yes, it could be an index. Yes. Okay. It's a method يعني, بس كمان برجع بقول لك قد ايه close to zero. يعني at the end you need to يعني هيدا الكرايتيريان حسن اللي عم تحكي عنه مثل هول الكرايتيريان اللي حكيت عنهم 1 2 3. You can calculate the determinant. It can give you an idea, but to know مظبوط ال condition we will see how to do it next time. Okay.
Okay.
So now, if I take here the following another example, now I will use the second strategy. Okay, I will do A times A minus 1 and see if it's close to I or not. So for example here, let us consider the following matrix. As you can see, it's a symmetric matrix. So you have 1, 1 over 2, 1 over 3 until 1 over 12. So now we want to test the L condition of this matrix. هلا هون كمان we can check if Cholesky is applicable or not. لأنه it's already symmetric, so we need to know if it's positive definite or not. هلا as I told you, أنا أكيد if it's such complex, I will tell you if it's positive definite or not. In case it's positive definite, A minus 1 will be much simpler to find. In case it's not, then we will use the conventional LU factorization method. Okay. هلا أكيد I don't expect that you will do such matrix, so I'm just giving you the result of MATLAB. So if I use MATLAB to get the inverse, I will get the following. I will get the following result, and then when I do the next step, when I do A times A minus 1, MATLAB will give me the final result. If I do A times A minus 1 in MATLAB, this is what I will obtain. And I should compare with I. Here, as I told you again, it depends on the accuracy you require. If you just want to trust, let's say 1 digit, it's accurate. For example, here, if you look at the diagonal, here it's very good. I got 1, I got 1. Here, I got a very close value to 1, up to 1, 2, 3, up to 4 digits. Okay, so it's fine. If your accuracy is just required to have 4 accurate digits after the decimal point, لحديت هلا it's fine. Now, for example, here, if I take this number here, this number I can just trust the 1 digit after the decimal point, because if I round to the closest number, it will be 1. Now, if I have to get a precision of 2 digits after الدوت ما كتير accurate لأنه هيدا if I round هيطلع 0.97 let's say, which is a little bit far from 1. So it depends on the degree of accuracy you want to have to say if it's for you if it's acceptable or not. بس هون عندي variation. I can say it's probably ill-conditioned. منا very ill-conditioned. Okay, but it is in a certain way ill-conditioned. Okay, and again you will look at your application. If it allows this should just trust one number after the decimal point, it's very good. I can go for it. If not, I should test all numbers كمان. يعني ما فيني وقف هون. I will, but it seems at diagonal I can trust the first the first digit after decimal point. It's fine. Now let us look at zeros. يعني I expect to have zeros everywhere, which is not the case. هلا هون for example the error is small لأنه عندي of the order 10 minus 7, which is كمان again if I just can trust 4 or 5 digits for these numbers after the decimal point, it's fine. But look here, for example, and the critical case here, for example, I have here 0.02. يعني if I have to trust 2 digits after the decimal point, it will not work with me, and I have 0.02. Okay, so I can say that this matrix is probably ill-conditioned because I cannot trust يعني more than 1 digit after the decimal point. Okay. Now the final example is for the final case. If I have a matrix and then I do a minus 1 minus 1. Okay. So if I take the same example of before and I do a minus 1 minus 1, I should get a value that is very close to a. Again, this is a. Okay, this is a here. Look at a. You have, for example, at diagonal 1, 0.333, 0.2. Just remember these elements to be able to compare. I will do for you the comparison with a minus 1 minus 1. So if you do a minus 1 minus 1 on MATLAB, you will get the following. You will see that these elements will vary, يعني ما حيكونوا exactly the same. So you have this. You have, for example, here it's 1 point. Here هونيك it's 1. Here it's 1.01. So if you want to trust 2 digits after the dot, you cannot trust them. You have here 0. Instead of 0.3333, you have 0.344. So again, here this the second digit. Yani I can trust the first digit, but not the second. And you can still compare all other terms. So depending on the accuracy you want, this might be acceptable or not. Okay. Any question on this part? So we defined several criteria to know if a matrix is ill-conditioned or not. Next time, we will see how to find a number with a certain number and calculation, the degree of illness of a matrix. So how we can find the condition number for a matrix. Okay, thank you. See you next time. Bye-bye. No, don't worry. No, Leia, of course, don't worry. I will give you something that is feasible.
Doctor?
Feasible with the time I gave you, yes.
Did you finish correcting all the tests?
No, I didn't. I really need time. I need